Hi, today we're going to be moving on into the next step of the redox unit. We're going to look at these things called half reactions, which I don't know if that gives away the whole story, but we'll see. So as a do now to make sure you really understand how oxidation numbers work and how they can change over a chemical reaction, I want you to take a look at this rather interesting chemical reaction between two acids and determine which element got oxidized and which element got reduced by assigning an oxidation number to each atom. Feel free to hit the pause button if you need to. So based on our previous set of rules that we talked about in the last video, we're just quickly going to go through and assign the ones that are easy. All hydrogens in a compound are a +1, all oxygens are a -2. All elements, like this I2, have an oxidation number of 0, +1, -2. If we need to do that math where we go through and multiply down to the bottom, that might be helpful for things like this HNO3 compound. This one probably doesn't need it. And +2, -2, and that equals 0, of course. That equals 0. So from here on out, we're just going to pick numbers that make this all equal 0. I don't see any ionic charges, so the sum of all oxidation numbers for any compound is 0. This should be then +5. There's only one N, so that nitrogen, is a +5. This iodine is a -1 because this has to add up to 0. This nitrogen is a +2. So, which element got oxidized? Which element got reduced? It looks to me like the iodine got reduced and the nitrogen, nope, doing that backwards. I just did that backwards. Boo. The nitrogen has an oxidation number of +5 and then it ends up with a +2, so that's reduction. Literally the oxidation number got reduced, it went down. The -1 to 0 is actually an increase, and that's why. So you could put I, you could put I2. I think I'm going to put I because as a reactant, the iodine is in a compound, so putting the I2 is a little bit misleading, just like you wouldn't put N2 for the reduction because there's no N2 in your reactants. So for today, we're going to watch a video, and here's the chemical reaction of what's going on, but I'm going to let you watch it just to see. It is, well, it's 3 minutes long. I wonder if I can play it back quicker. Yes. The only reason I want to play it back quicker is because, well, you'll see. It's a lot of mixing. But record any observations you make over the course of the video. You can see some color now. Something's getting thrown in. I can see this thing here. It looks like a little bit of a string up at the top here. But let's watch. This is why I played it back at 1.5 speed. I don't know what color that is. I'm going to leave it to your guys' judgment. I don't quite know what to call that. But something's happening. It's that purple again. It's that permanganate, so that probably has something to do with it. Okay. Okay. So that's not purple anymore. I'm going to say clear yellow solution. Now, these substances here, these little balls of string, they're not string. That's more steel wool. First off, 2 words. Second off, I can't spell. Now this steel wool here is excess, right? That's still your reactant left over. So the products here are the clear yellowish solution and whatever that is. So I included a reaction for everyone to see. The two reactions are absolutely identical. The only difference is I went through and I removed the chemical species that don't participate in the reaction, spectators, to make things a little bit easier, because I want you to try and balance the reaction. Like, that's why there are blanks. So take a second and try and do that. Try and put some coefficients in there to make this a balanced chemical reaction. Excellent. So I see 4 oxygens, so I should put a 4 there. That would mean 8 H pluses there, and we're done, right? Well, yes and no. Turns out that chemical equations need to be balanced in mass, charge, and energy. And I like pulling this question. This is clearly from an old Regents, almost 10 years ago at this point. And the more times this gets watched, the older the question gets. But looking at this question, you can see that, yeah, there are irons and aluminums, but this reaction shows the same number of irons and aluminums. This reaction shows the same number of irons and aluminums on both sides. This one shows the same number of irons and aluminums. This one doesn't, so it's clearly not the answer. So, but that's showing which ones are balanced in mass. And we did talk about the idea of delta H and balancing reactions in energy, but we also need to make sure that the total charge is balanced. And that is to say, you know, we said that no matter can be created or destroyed. Electrons can't be created or destroyed. Charge cannot be created or destroyed. You can have a particle increase in charge, but something else has to decrease in charge to compensate for that. So what we're going to do here is, if we look, the total charge of the reactants as they're shown is +3, and the total charge of the products is +5. So that can't be our answer. The total charge here is +3. I'm going to try that again. Go up and down. And then the total charge here is actually 2 plus 9. 3 times 3 is 9. That's +11. So that's not right. So hopefully our number 3 here is the right answer. So the total sum of the charges here, I'm going to do a square bracket, is +9. 3 times 2 is 6. 6 plus 3 is +9. So that's our answer. So in looking at these reactions, not only do we have to balance them for mass, we have to balance them for charge. If we go back to the reaction that we saw, this is the same exact reaction. I had written an 8 and a 4. Well, does this balance the reaction for charge? No, let's add them up. We have 8 pluses, we have 1 minus. That's a +7. We have 1 3 plus and 1 2 plus. That's a +5. Well, it looks like we need some more pluses in our product, so I could, I don't know, put a 2 there. But that, and then that turns that into a +7. But you can't do that, right? You can't just put a 2 without putting a 2 here, which, because of the manganeses, which would then make that a +6. And if I put a 2 there, that has to be an 8. And if that's an 8, then that's a 16, and that's 16 pluses and 2 minuses, so that's actually a +14. Maybe, so we need more of these. I don't know, put 3 there, and 3 there, and that's 9, so that's +6. +3, the 8. No, I don't think I can balance this just by counting. I think we have to do something additional. And when it comes to redox reactions, frequently this is what happens. Yeah, many redox reactions can be balanced by just, you know, looking at atoms and counting them up. They call it balancing by inspection. But many reactions cannot be. And if I were to go all the way back to our original reaction, this reaction, I want you to try and balance it. Try counting it up. There are chlorines in 4 different substances. There are hydrogens, well, the hydrogens are actually just in 2 places. There are potassiums in 2 places. But like, try and balance those chlorines. It's not gonna work. Like, you might be able to figure it out. If I challenge you to do so, and if you figure out a series of coefficients that work, by all means, put it down in the comments. I would love to see what the balanced reaction actually looks like. But also, by the end of the next video, we'll be able to balance it all together. So I'm happy to work through this process with you instead of just trusting you to figure it out on your own. So let's take a step in and just take a look at the chemical reaction as a whole. Like the do now, I want you to take a step back, and this is a long process. So we're only going to do half the process today. The next lesson will deal with the second half of the process. But which chemical was oxidized and which was reduced? Luckily, since I got rid of all those spectators, the only substances that we actually need to do calculation for are the permanganate ion and the water, because for this H+, that's a +1. For this iron, it's a 0. For this iron, it's a +3. This is a +2, +1, and -2. These should be 2+ and 3+, shouldn't they? Oh well. And then here. So in MnO4 minus, we're going to call an oxygen as a rule -2. That's a total of a -8 equals -1 x. So x minus 8 equals 1, x equals 7. There's only one manganese, so +7. +7 minus 2. So which substance got oxidized, which got reduced? I think the iron got oxidized and the manganese got reduced. Based on what I see here, the manganese goes from +7 to +2. Usually when you have a permanganate, the permanganate is what's getting reduced because +7 is the maximum oxidation number possible for a manganese. That stuff's pretty reactive. That's why it's so pretty. No. Frequently, the prettier it is, the more reactive it is, and the more poisonous it is. But, well, how do you know? Well, this went from 0 to +3, and this went from +7 to +2. So maybe already you're getting some ideas of how to balance it, but that's okay. So we're going to say, we're going to define this half reaction as a chemical reaction showing just the oxidation or reduction in a redox reaction. It might feel like even less than half a reaction, but that's okay. And the way we're going to do this, some textbooks, some other sources might disagree with me on this, but go with me. This is the simpler way to do it, even if it involves a little bit more thinking down the road. We just have to write pretty much what we wrote already. We know the iron got oxidized, we know the manganese got reduced, but we're going to find the oxidized and reduced species and add electrons to balance the charge. So what I want you to do is I want you to not only just write that iron was oxidized, I want you to show iron's oxidation state changing as a result of the reaction. Now again, we're only showing half the reaction. We're showing less than half the reaction because anything that didn't change is gone. But we're only showing the element and its oxidation number and how it changes because of the reaction. These two half reactions are not balanced because, like we said, everything has to be balanced for mass and charge. They're balanced for mass. There is one iron and one manganese and one manganese, but the charges are wrong. And the way you fix the charges is that you add electrons to balance out the charge. So here our sum is 0 and here our sum is +3. We need to add electrons. Add electrons to the more positive side, since adding electrons will bring down the total charge of that side of the equation. So if I add 3 electrons over here, now the sum of all the charges is 0. The sum of the charges is 0, the sum of the charges is 0. That is a balanced oxidation half reaction. For this one, we're going to add 5 electrons to the reactants so that the sum of the charges here is +2 to match the +2 on the products. So the whole idea is, we said oxidation is losing. Well, if we're losing electrons, that means product, and reduction is gaining. And if we're gaining electrons, that means reactants. So if you're shown a half reaction just by itself, you can pretty easily identify it as an oxidation half reaction or a reduction half reaction just by where the electrons are located. But this is the process we go through. I have a couple practice problems and we're about done. I kind of want to start with the one on the bottom, the multiple choice one, because of what I just said. which half reaction equation represents the reduction of iron 2? So if it's the reduction of iron 2, we know that because of reduction, we're going to see electrons on reactants. And iron 2 means an Fe2 plus in reactants. So we can immediately get rid of these two choices because iron 2 is not in the reactants. We can get rid of this choice because iron 2 and electrons have to be in the reactants. And so just to make sure, choice 2 is not only iron 2 getting reduced, gaining 2 electrons, but also that the mass and the charge are balanced. Don't forget, electrons don't have charge. Okay, don't have charge. It's a negligible, sorry. Electrons don't have mass. Don't have mass. The mass is essentially 0. It's not 0, but it's not 0, and it's small enough that we call it negligible, and we never really include it in our mass balances. Knowing all of this, you can hit the pause button for 30 seconds, a minute, 2 minutes. You have 2 reactions here. For the one on the left, I want you to figure out both the oxidation and reduction half reactions. And for the one on the right, I just want the reduction half reactions. So just like before, we're going to go through and we're going to assign everything an oxidation number. You can figure out chlorine here is a +1, chromium here is a +6. For the math to work out, that means that the chlorine changes from a +1 to a -1, and the chromium changes from a +3 to a +6. So that means that the oxidation is going to be the chromium, and the reduction is going to be the chlorine. So let's write our half reactions. Chromium goes from +3 to a +6. Chlorine goes from a +1 to a -1. We have to do some algebra. 2 electrons should be needed to accomplish that, and 3 electrons will be reduced up here. It doesn't really matter if you write the electrons before or after, right? As long as it's on the right side of the arrow. That's the more important part. For the reduction that occurs. So the key to understanding this problem is that when you have an element and there's no charge shown, that's a 0. So we're going from a +1 to a 0 and a 0 to a +2. So this one is the reduction and that one's the oxidation. There are 2 acceptable responses for this because these coefficients, it's always a question, do you include the coefficients? You don't need to, but you can. So for the reduction, I would say that my answer, given how I've been showing you guys, would be that silver ion plus an electron becomes silver atom. You can put the 0, you don't have to. If you said instead you wanted to drag down the 2Ag+, you still have to have the charge balanced out and the mass balanced out, so that would need 2 electrons. So there's actually like this little bit of additional stoichiometry in there if you want to think about it this way. The idea is that 1 mole of silver ions will gain 1 mole of electrons to make 1 mole of silver atoms. By the same token, 2 moles of silver ions would need 2 moles of electrons to become 2 moles of silver atoms. So in summary, I don't want to start with an O. In summary, ooh, wow, how to jump to pen. Oh no, go back. I said in summary, pen. Half reactions show just oxidation or reduction. They show one element, even if in compound, and show the electrons gained or lost, balance for charge. So in this example, we're going to go through one more as a bit of a summary, but I also wanted to show you something pretty cool. Let's go through and assign some oxidation numbers. Bromine here is a 0, potassium's a +1 because always +1, -2 +1, that adds up to 0, +1 -1 because potassium's always a +1, oxygen's always a -2, None of these are the exceptions. Hydrogen's a +1. That means this bromine's a +5. Hopefully that wasn't too fast. You can go back and listen to it again. What you do see is after you do enough of these, it does start to become smoother, that you start seeing patterns and things start popping up. Oh yeah, BrO3, bromate, it's a +5 on the bromine. That makes it pretty reactive. I mean, this reaction still happens, but which substance got oxidized, which got reduced? Well, the potassiums went from +1 to +1 in all cases. The hydrogen went from +1 to +1. The oxygen went from -2 to -2, -2. It's the bromine. Bromine went from a 0 to a +5. Bromine also went from a 0 to a -1. It's both. And this is possible. It's unlikely. It's a more rare reaction. It's possible, though. It's called disproportionation, where the same element is both oxidized and reduced. So the bromine and the bromine. And this yields an interesting discussion, only because it's this last thing to mention. When a halogen or a diatomic undergoes a redox reaction from the element or to the element, the question of whether or not you show the two is always on the table. And just like we saw with the previous practice problem, it doesn't matter. You can do either. So I'm going to show two sets of answers. First, we're going to just use the elements. Bromine 0 becomes bromine +5 plus 5 electrons. Bromine 0 becomes, nope. Need to erase. Plus an electron becomes the bromide -1 ion. That's one way to show it. The other way to show it would be to say, this is a diatomic element. I know it's a diatomic element. I'm always supposed to show it's a diatomic element, and I'm going to. That being said, though, you're going to need to show 2 Br +5s because balancing for mass. You're always going to show that conservation of mass, which then means you need to show 10 electrons. You can't reduce this reaction because the coefficient on the bromine is a 1. For the reduction, you'd show something very similar. Again, you'd have to add 2 electrons and you'd make 2 bromides. But it works the same way. Both of these would be called acceptable options. I personally kind of prefer the second one a little bit because it does acknowledge that the diatomic is in fact a diatomic. But that's everything. Thanks for watching.